Take a look at your phone. How does a silent block of glass and metal calculate billions of numbers a second and glow perfectly? The answers are found in the study of how atoms behave when they are locked together in a solid. This textbook holds the blueprints to understanding how these materials work. To make sense of it, imagine the inside of a microchip as a highly customized microscopic dance club with extremely strict rules. Everything your computer or phone accomplishes is dictated by the physical layout of this tiny room. This floor plan is a crystal lattice. It is a rigid grid where every atom is securely locked in place. We custom build this room atom by atom, expanding to fit exact specifications. We also swap out standard tiles. This doping invites special guests. This customized crystal lattice is a meticulously designed environment built specifically to control energy. Moving to Chapter 2 of our guide, we transition from the physical structure of the building to its electronic properties. Our club has two distinct levels. On the ground floor, the valence band, the crowd is packed shoulder to shoulder, vibrating with no room to walk. Above is the VIP balcony, the conduction band, completely empty. The void between them is the band gap, with no easy way across. Electricity requires movement. To get current flowing, we have to find a way to get dancers across that gap and up onto the balcony. Doping changes the rules. Special guests are placed directly onto the balcony, sprinting side to side. Conversely, removing dancers from the packed ground floor creates empty seats called holes. As the gridlocked crowd shuffles into these spots, the open seats appear to travel in reverse. By engineering these two floors and carefully guiding the traffic between them, scientists gain the power to start and stop the crowd's movement at will. That precise ability to switch between flow and gridlock is exactly what allows a computer to process information. Now we look at how this electronic architecture interacts with light. Watch when a flash of external energy enters. Incoming light strikes a single dancer on the packed ground floor. That burst of energy provides enough power to leap over the band gap and land on the balcony. This process, called absorption, makes solar panels work. Semiconductors can catch sunlight from the outside world and convert it directly into useful electrical movement inside the chip. But what goes up must come down. Eventually, a dancer running on the balcony loses momentum and spot an empty seat waiting on the ground floor below. Watch the dancer drop from the balcony. They plummet across the band gap, slotting perfectly into the open seat, a process called recombination. No longer needing high energy, they release it. Hitting the ground floor, that extra energy bursts outward as a flash of light, luminescence. Multiply that microscopic drop by billions of times every single second. That collective release of energy is exactly what happens when you turn on an LED bulb or look at a glowing digital screen. By perfecting the layout of the crystal room, managing the traffic between the two floors, and controlling those precise energy jumps, semiconductors serve as translators between physical structure, electricity, and light.